Hello and welcome to another episode of the DigiTeacher. In this week's episode, I'd like to look at the whole question of levels of abstraction in computer education. So abstraction is seen as a particular problem in computing because it is notoriously difficult to teach. So if you think about it, you're thinking about the theory of computing. You have a whole bunch of acronyms. How on earth does a computer itself work? How are numbers represented? There's a lot of abstraction there. So of course the way a computer works is highly concrete, but understanding it involves levels of abstraction which are very difficult to get your head around. I have no idea, for example, it boggles the mind how files save on a spinning disk. It's just incredible to think about. So high levels of abstraction. When it comes to coding, you have a similar kind of problem. So although the program itself is very concrete, very much in the context and so on, and experienced coders will not think of that as very abstract at all. When you're a beginner coder, what's a for loop? It's quite difficult to understand the concept of what it is and then to apply it. So that kind of gap between theory and practice is quite a gulf, and it makes teaching computing very difficult, learning computing very difficult. And so is there anything that can help us along the way? Well, the idea of levels of abstraction in computing is something which has been written about quite extensively, and there's some taxonomies out there for how we view this. But today I'd like to look at a particular paper that was brought out by some academics from universities in the London area, and I'll get to that in a moment. And they take these taxonomies of levels of abstraction in computing and they kind of pull them together in something which is more easily understandable for teachers to apply in the classroom. So let's have a look at the paper. So the paper is called Abstraction in Action. K5 teaches use of levels of abstraction, particularly in the design level in teaching programming, and it's brought out by Jane Wade, Paul Curzon, Marsh Sentence and Hadwin Bennett from Queen Mary University and King's College London. It came out in the International Journal of Computer Science Education in 2018. So let's have a look at what this paper is saying about abstraction. So what they're doing here is pulling together and comparing and taking similarities of three different taxonomies: the PGK hierarchy, the abstraction transition taxonomy, and the abstraction through simulation model. So the basic idea is that you have different levels. The one level is of the problem itself. So this is a general description of what the computer is supposed to do. So this will be in kind of ordinary language, and what is needed, what is required from the program. And this will involve a general understanding of the world and the problem area and what to do about it. Then what you do is you need to design a solution, and this solution design is kind of similar to an algorithm. It might be a flow chart of what's supposed to happen. It might be involved when you're programming it. You might want kids to do trace tables or whatever techniques you're using to understand what it is exactly that the computer is supposed to do. This kind of reaches a level of pseudocode, and then so it's bringing in computer science speak. Then you have the level of the code itself. You actually code in a particular syntax, a particular language, and then you execute the code. So how does this help us? Well, if you've taught coding at all, I think you'll recognize that one of the biggest areas where students fall down is in the overall design of their program. So students are often quite good at accurately coding something. They can take a conditional statement, for example, and code it quite accurately. Sometimes not, but most can. But very often how that fits into what the program is supposed to do is where they fall down. In other words, they don't have a really clear sense of the overall algorithm and how the program is supposed to work overall. So in this paper, that's focusing on the kind of design element. which is really at how you take a general problem and you translate that into more computer speak before coding it itself. So it's kind of at that design of an algorithm. And I think this paper really points to that as the area where teachers can help the most. If a teacher can model that for students or scaffold learning around that for students. So in the paper they say that this kind of proto-algorithm design work in designing a computer program is very similar to kind of planning for writing. So just as planning for writing helps students become better writers, then planning for the program, designing algorithms for the program, will help learners become better programmers. And I think they demonstrate this in the paper quite successfully. I think the other issue we need to look at is how students arrive at that overall solution. So if you think about something more along the lines of problem-based learning, where you want to get students to look at the world, identify a problem, analyze and research that problem to find out what's wrong and what needs to be fixed, and then design a solution which can then be coded into a prototype solution. So for example, wasting energy, you might well say, well, lights are on when they don't need to be on, therefore let's hook it up to a movement sensor, or only put the light on when it gets dark, that kind of thing. And then you kind of worked out, well, that's what's necessary, but what students really struggle with is then taking that general understanding, that kind of at an abstract level, that's the problem, and that's how I want to solve the problem. They really struggle to put that into a kind of design, an algorithm. And I think this paper really kind of points out that that's the area that needs the most work. Both when you're looking at the world and trying to identify a problem and identify a solution, it's kind of moving through those level of abstractions. Students can usually identify the world around them, well, it's a problem, the lights are on. But they struggle to kind of put that in more scientific language, more abstract language, more abstract understandings, more scientific understandings, more logical understandings. If the light level is less than a certain amount, we must switch the light on, otherwise the light must be off, kind of thing. It's at that level, both going up the scale to realize what the problem is and then to design the solution by creating an algorithm. It's kind of at that just fairly abstract level where you're translating an understanding of what's going on in the world at large into something that is realizable through a computer program. That's where the attention needs to be. So if we think about what a student needs to do, they need to frame the problem, moving from the kind of very concrete everyday experience, coming to understand the world coming to understand the problem in more general terms, eventually kind of modeling it in terms of either logically how it should be set out, if this then that, etc., understanding any of the science that's involved, any maths that has to be involved. And then they've got to code that solution, and then they move down from more abstract level of understanding what the solution is, designing an algorithm, bringing in more computer science kind of speak, flowcharts and pseudocode, trace tables, whatever it is, and then actually doing the coding in a particular syntax. Then they need to execute the program, observe it, test it, and then debug it. So you've got a movement from very contextual, observing the world, up until you have a very kind of much more abstract understanding of the problem. You design the solution in quite abstract terms, but then you put it into computer speak. You design a flow chart, an algorithm for solving the problem, and then you code it, and then you run the program and test it. So you've got this movement up and down, from very concrete to abstract, and then from abstract back to concrete. I think this kind of model for understanding what it is that we're actually asking students to do when they code a solution to a problem is quite helpful. Now the big issue is, how do you tailor your pedagogy to scaffold that learning and support that learning? because people don't learn to do this on their own. It's not something that arrives, straight from the head of Zeus into your head. It's something which needs to be learnt. It's something that needs to be practiced over time. You see it modeled. You get taught different techniques for doing it, different thinking strategies, different skills, and then you can start to learn to do that. Once you've started to be able to do it in some context, you should be able to generalize the skill. Well, I've solved this particular problem. Let me take the same strategies and ways of thinking and ways of working to solve another problem. So I don't want to get into particular pedagogies now, but I think that's quite a useful framework for helping us think about our teaching and what we need to do and what we need to focus on, what we need to concentrate on when we are teaching. And as I say it, I think it's that level of the algorithm that really, really, really is crucial. That's where kids come unstuck the most. Well, I hope you found this video useful. And if you have, please please share it, and subscribe so that you never miss another episode again.